Welcome to the third part of the Formal Languages and Automata course.
Stop. With your feet on the air, your head on the ground.
In the last lecture, we presented alphabets, which are the basic building blocks used to build strings, which are just sequences made up of these alphabet symbols. May I remind you here that the empty string is denoted by the symbol epsilon. Then we said that languages are just sets containing these lovely strings. May I also point out that the empty set, denoted by either this symbol or this notation, is also a valid language. We also mentioned the string catenation operation or concatenation. This can be defined by induction on the structure of the first string. In particular, if the first string is of the form epsilon, then concatenating epsilon with the second string t would give you back t. If, on the other hand, this first string is of the form alpha const with some continuation s, then the concatenation with the string t is alpha const the continuation s catenated with the string t. For example, if we wanted to concatenate the string AB with the string AA, we would realize that the string AB is of the form alpha followed by some continuation s. Therefore, we have to apply the second case here. And this tells us that the answer is A cons the concatenation of the string B with the string AA. Now, the concatenation of the string B with the string AA is once again something of case 2 here. So this is equal to B cons the remainder, which in this case it is the empty string, concatenated with the string AA. At this point, we apply the first case, and this part here yields us just the string AA. This means that the final result is the string ABAA. We can define other operations on strings. One such example is string exponentiation, where you take some string s and you raise it to the power n, where n is some natural number. We can define this operation by induction. However, this time we use a slightly different form of induction. It's called numerical induction. Concretely, if you take some string s and you raise it to the power 0, you get back the empty string. If, however, you take s and you raise it to the natural number of the form k plus 1, then The answer is S concatenated, this is string concatenation, to the string S raised to the power k. Note that this natural number k is strictly less than this natural number k plus 1. This is why induction works. As an example, if we take the string AB and raise it to the power 2, then this is equal to the string AB concatenated with the string AB raised to the power 1, because note 2 here is of the form k plus 1. But what is AB raised to the power 1? Well, it is once again AB concatenated with AB raised to the power 0. And what is AB raised to the power 0? It is the empty string. We get this via the base case of the inductive definition. If you concatenate these three strings, you will obtain the string AB, AB. Let us turn our attention back to languages. In particular, how would you represent a language? If the language is finite, you could just list all of its elements one after the other, S1 followed by S2. If the language is infinite, you could also try this process. By the way, this process is called the process of enumeration. However, it will take you a very, very long time. So I wouldn't recommend. Instead, a more convenient way how to denote infinite languages is via predicates. May I remind you again what a predicate is? A predicate is just a function that maps to the Boolean domain. We've seen some predicates in the previous lecture. Do you remember has been? So we can use this predicate to define a set that describes all the strings that contain at least one occurrence of the letter B using the predicate has been. So it is all the X that satisfy this predicate. We could also use our previous functions in conjunction with other operators that you might be familiar with to define other sets. For example, the set here denotes the set of all the strings whose size is greater than or equal to 3. This last set here denotes the set of all strings, or rather it denotes the language of all strings that contain exactly 4 occurrences of the letter A. Of course, we can do more, a lot more. For example, I can define the language made up of the pattern AB, 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 where at least this pattern recurs twice. It can occur more than twice, but at least I should see AB, AB twice. I can also define the language whose strings always start with an A and end with an A, and whereby the middle element S must have at least one occurrence of the letter B. It could have more, but at least it must have one occurrence of the letter B. Notice that sometimes writing these strings can get a bit tedious, so we define a shorthand notation to describe these languages. Note also that we are using a convention here where concatenation binds more tightly than exponentiation. This simply means that whenever we write something of the form ab to the power n, that means that the n, the exponentiation, refers to the entire string ab. If, however, we want to refer to just the b, we use bracketing. Oops, I just realized that I have a typo here. Silly me, happens to the best of us. So here, instead of len, it should be size. Size is the function we defined earlier. But let's move on. Since languages are also sets, we immediately inherit all the operations that apply to sets. In particular, a language L1 could be union with some other language L2. We could also define the intersection between two languages, or set difference. Finally, it is also convenient to be able to use set complementation, which takes anything else that is in sigma star apart from the elements, in this case, of language L1. Together with these operations, we inherit all the identities that apply to sets, and a whole bunch of complicated words that you can use to impress your favorite girl, boy, or non-binary person you might be interested in. In particular, languages are commutative with respect to intersection and union. They also happen to be associative, distributive, and they also observe the De Morgan laws. Languages also observe the complement rules, and they also observe the involution rules. They observe the dominance rules, as well as the identity. And wouldn't you want to add idempotence to your dating app profile? Maybe not. But languages also observe the idempotence rules. Since languages are a special kind of set, we can also define operations that only operate exclusively on languages. One such operation is the language concatenation operation. The concatenation of language L1 with language L2 is a new language whereby every element of this language, that is, every string of this language, can be split into two parts, where the first part belongs to L1 and the second part belongs to L2. For example, consider the case where L1 is the set containing two strings, the string AA and the string BA. And L2 is another set that contains two strings. The first one is B and the second one is BBB. Then L1 concatenated with L2 is the set containing four elements. The first element is the string AAB. Notice how AAB is obtained. In fact, you can split AAB into two parts. with the first part, A, is an element of L1, and the second part, B, is an element of L2. The same applies for all the other strings in this set. Did I hear the word easy peasy? Time for some exercises then. Try them out. Moving on, we can also define the language exponentiation operation, whereby we raise a language to some exponent n, where n is a natural number. Once again, we can define this operation by numerical induction on the natural number n. If you raise language to the natural number 0, then this is the set containing the empty string. It's not the empty string because you have to return a language. So it is the set containing the empty string. If you raise a language L to the power k plus 1, then this is the language concatenation of L with L raised to the power k. Sometimes it's also convenient for us to define L star, which is just the union of all the exponentiations for that language. This gives us more identities and complicated words to flirt with. For example, language catenation is associative with respect to the union. Actually, I think this is actually distributive. It distributes over union. My bad. You also have identity rules and dominance rules for both language catenation and also language exponentiation with respect to union and intersection. You can probably figure these out. Of course, not every identity holds. Here are a few that don't. Your job is to try to understand why they don't hold. Try them out as an exercise. Are you getting tired sitting down? Do you have cramps in your buttocks? Here are a few exercises. Enjoy.